Okay, that works. As long as it's not me. How is this ever going to work? Oh, yeah, dinner for one. Yummy, yeah. At that point, like, of course, I'm not going to die of that. That's what you're saying.
Hi everyone, welcome back. We're so excited for our afternoon session. Starting with Jason, our afternoon hostess, Charlemagne from
Hello everyone. Hope everyone had a fun poster session. So I'll be your host for the afternoon. I'm Zhaofeng Wu from MIT. And for the first speaker for today, we have Jason Weston. Jason is a research scientist at Meta AI and a visiting research professor at NYU. He earned his PhD in machine learning at Royal Holloway, University of London, and AT&T Research in Red Bank in 2000. Jason's publications include Best Paper Awards at ICML and ECML, as well as the Test of Time Award at ICML 2008. And take it away.
Thank you. Yeah, so I've been working on LLMs for a while, or even before that, I was working on SVMs. So in the beginning, there were models with learnable parameters. Well, even before the 2000s, but in the 2000s, because I talk about those because I was there, we were doing SVMs and we were training their weights. In the 2010s, we still had learnable parameters, but more of them. We kind of got neural networks back in the mainstream. We had AlexNet and transformers later on in 2017. But the architectures, the code to do this training and inference, the data that we use for training, validation, the loss function, so the updates, the training algorithm, these are all fixed by the human researchers for that particular architecture. Of course, we're always changing them. That's the research field, right? Where we try and work out what is the next architecture, and we write the code for it, and what is the next training set, and so on. But they're fixed in the sense that the model or the AI algorithm, whether it isn't learning them while its parameters or weights are being learned. And advances in AI have been driven generally by giving models greater power to self-improve. But that's been mostly in that more weights dimension, so more parameters, and then allowing it to self-improve by training those weights. So we have like the famous kind of scaling hypothesis. In the seek-to-seek paper, so 2014, you have Ilias, Skiva, Oriel, and Kwok have this conclusion slide I have there. You have a large big data set and you train a very big neural network. Success is guaranteed, which is a bit glib, and yet in the preceding 11 years, that's kind of what happened. And here's a graph here of all the LLMs and getting the models bigger. Now we have these more MOE models, which are pretty big too. But again, the architecture, data, loss function, and update algorithm were mostly fixed until kind of recently. So which leads me to this more self-modifying hypothesis, where I'm saying that it's inevitable that eventually AI will help train itself in all meanings, so not by just learning its weights with a fixed algorithm data, but by also creating its own data, which has already started. So we call that synthetic data, right? And say llama models and other models, a lot of the data they're trained on is synthetic data, so created by the model itself. They'll also work out how to evaluate themselves and tune their loss function, so that's already started as well. I'll talk about that. And then finally, in a more sort of meta, even more complex way of training themselves, I expect them to design improvements for themselves in terms of their algorithm and code required, which I'm calling here self-modification, which we have kind of the glimpses now of like people starting to work on that, but I would say that one is the one we're not there yet. But I'll just have some slides on why I think that's the path. But for most of the talk, I'll start here first and talk about models creating their own data and evaluating themselves and achieving their loss. So I kind of started on that path last year, so in 2024 January, we put out a paper called Self-Rewarding Language Models, which tried to do some of those things. So the goal is an AI that trains itself as much as possible. That's sort of a slide from then, but we didn't have the bit about self-modifying, but we did have the bit about creating new tasks to train on, so challenging itself, evaluating whether it gets them right, and that's why it's called self-rewarding, and updating itself based on what it understood, and kind of ask the research question, can this help it become superhuman, say in a setting where a human isn't able to provide those rewards very well. Maybe the model can actually do a better job in some cases, and you get this virtuous circle. So yeah, just go through some slides from that time. We were saying that current LLMs are approaching human level on a variety of tasks, and there's a reason to believe that future LLMs will surpass human performance. It's kind of a sort of alignment challenge. So the problem with the standard reinforcement learning from human feedback approach is you've got humans in the loop, so you might have them collecting the SFT data and labeling pairs to training your reward model. But as the LLM responses get better and better, I mean, let's say it's in the medical or healthcare domain, as was talked about earlier, or the legal domain, or some domain where the average human is probably going to be actually much worse than the LLM. You're going to need an expert human, like starting to be vanishing the few expert humans, let's say in the math domain, that are better than the LLM. This is getting harder and harder for us to label this data. So the way we then propose to do this is, let's say we want to get the model to label this data. What better model to do it than the most powerful one we have? And the most powerful one we have is probably the one we're already training to try to do all the tasks, because now we train them to be multitasking, right? That's the instruction following task, is to try to take an input, a prompt of any kind of task and to fulfill it. So we want to have this instruction following capability, but you can look at the ability to evaluate how well it's doing is also an instruction following task. So that's called LLM as a judge. You can give an instruction, a prompt, which has an instruction, has a model response, and then the task is to assign a score of how good the response is based on some rubrics. And that would be LLM as a judge. And then you can plug this in. So this is the same language model that you're training, right? It's going to be doing the self-rewarding. So you plug that in a loop. You can also get that language model to generate new training data, well, again by prompting. You would then, in this loop, get it to, given those prompts that it's generated, to generate a set of responses, to assign rewards using the LLM as a judge, and then from those scores you can generate preference pairs, and we use their DPO training and then repeat the whole loop, so in what's called iterative DPO. You could do something other than DPO, but that's what we use there. And then we showed that on the iterations of this self-rewarding, it's getting better on each iteration until it saturates. And at the time, that drew some attention because even though that was done by a PhD student at NYU, Asia, the performance on some benchmarks like Alpaca eval and instruction following benchmark were getting pretty close to GPT-4, some production language models. the other thing that we showed there is that its self-rewarding capability, because it's getting better on each iteration instruction following, is also getting better at providing self-rewards, evaluations. So that's, for example, this pairwise accuracy across iterations is improving a little bit. But the reason we think it's saturating at, say, 3 iterations is because that is improving enough, and we didn't really kind of explicitly push that in that work. So we have some follow-on work where we try to do more of that. In April of last year, we then sort of generalized that to also being able to do reasoning tasks, so generating chains of thoughts before you output the response, and doing this iterative training loop where you're then improving the chain of thoughts at each step. So we call that iterative reasoning preference optimization. So you can see the picture looks pretty similar. A major change we made was that the rewards we computed, we actually dropped the LLM as a judge and simplified it, and we only used verifiable rewards that just say whether the math problem is correct or not. So ignoring the chain of thought and just looking at whether it's correct or not, and then rewarding that as a chosen instead of a rejected in the DPO training pairs, and then iterating. So and it just ended up that that path, that research path, is kind of exactly the same direction that O1 and R1 went as well. So yeah, it's showing on GSM-8K that the performance improves as you train these chain of thoughts across iterations. Similar results on some other data sets like ARC and Math. So O1 was released in September. They didn't say how they did it. DeepSeek R1 was released 2025 January, and they said they were doing something like this, doing verifiable rewards. They used GRPO instead of iterative DPO, but obviously got a lot of things right and scaled it to do that thing. And then Mark Chen from OpenAI came out with a tweet saying, oh, that's what we were doing too, but they didn't have a paper. But yeah, it's just kind of an interlude, I guess, that this whole kind of loop can include reasoning training as well. I'm going to skip those. Another direction that we tried to look at was, instead of using language tokens to do the chain of thought, tried to do that vectorially as well. We call that coconut. That's not really as well developed, but an interesting direction to go. And then, of course, you can do this thinking for any kind of task. You don't have to do it just for a verifiable task, like a math problem. So we generalized that back in October, called it Thinking LLMs. And there we basically put back the LLM as a judge that we removed. So we got it back again from the self-rewarding work. We just simply begin with a prompt that asks the language model to organize its response into 2 parts, the thinking part and then the response part. We cut out the response part and use the LLM as a judge only on the final response part for any task to say whether it's good or not. For example, now we can judge, say, a poem in this manner, having some thought steps, planning how to write the poems here on the right-hand side. So you don't need this to be a verifiable task. And then we train that again in this iterative, self-rewarding way, and we do see improvements over not having these reasoning step thoughts, which is a direct baseline here in the bottom right. So I think that's a pretty interesting direction. There's some text in the DeepSeek R1 paper, although I didn't really fully get it. I mean, obviously they haven't released their data and stuff like that. It seems to suggest they might be doing something like that too. And then, yeah, to get back to the point of the self-rewarding part, the LLM as a judge, saturating and not directly being improved. by just creating random few-shot prompts and then doing iterative DPO. We introduced an added loss function which we call meta-rewarding, where we try to reward the rewards. So now we still have a single language model, but it acts both as an instruction following agent, an actor as a judge to assign rewards to the responses from those instructions, and as a meta-judge, which assigns rewards to the ability to assign judgments. So we call that LLM as a meta-judge instead of LLM as a judge. So you can see the prompt we use here, where there's a rubric. There would be the user instruction, a response from the model, and then 2 judgments. So that would be the text of the LLM as a judge, which makes the judgment, and then a score. And then this prompt asks which of the judgments is correct. So that's kind of a meta-judgment on the judgments, right? And then we sample a number of judgments and run this meta-judgment. We compute an ELO score over the judgments, and then we take the highest ELO score and the lowest. And those are going to be chosen or rejected for DPO training to try to train the judge, its ability to judge via these meta-judgments. So that gives us 2 types of training data. Now we have the original actor data, which we have for self-rewarding, and this judge data. And when we do that, we do see some improvements over the original self-rewarding approach in terms of, say, LC win rate on Hacker Eval, and also on Arena Hard and some other data sets. So, there's a plot here. Yeah, we do see like less saturation of the model across the iteration. So I think that's quite promising if we can have basically more ways to try to make the model train itself and stay consistent in various aspects. Okay, and now I'm going to get back to the wildest and wackiest point I was making at the beginning of the talk, which is that I think beyond just doing those things that I said, creating its own data and tuning its loss and trying to train the loss, maybe these models can actually design completely new architectures, the code, and then run experiments and things like that, so that we can actually close the loop on the whole of AI research and completely remove ourselves from the job. So now, we already had the start of this AI scientist research. LLMs are already quite good at coding, at least in some limited ways. Vibe coding is now a thing. I mean, I use that personally as well. So isn't the obvious thing to make these AIs self-developing and self-discovering using these tools when we get them good enough? I think the cool thing about that is, people talk about the flaws of LLMs, for example, Jan Lekan, who I work with, and they are flawed, but we only actually, if this self-modification hypothesis is true, we only actually have to make these models good enough to start this loop, because then we can find new architectures and code them, and we'll have better models, so we can get the models to improve themselves. So I feel like we only need to get to this point. I don't know if that sounds wacky to you, but I started to think that could be true. So then what you would need is these models to come up with ideas how to improve themselves, design new algorithms based on those ideas, write the code, design experiments, create synthetic data, train models, evaluate models, improve their code, and iterate this whole thing. Now, I think we're a bit away from getting all of that to work, but even if the first iterations aren't perfect, you could still have, being assisted, like humans assisted in each of these points to make the research cycle faster. And we're already seeing that, for example, in coding, right? A lot of coding is being AI assisted now to help make us faster, so why not in all of these bullet points here? but models doing all of it, would somehow be closing the loop. Yeah, so some evidence along this path I just mentioned. Code assisting as works. At Google they say more than a quarter of all new code is being generated by AI and then reviewed and accepted by engineers. So we're already at that stage, right, where we have AI assisting vibe coding starting to work. These things are only going to get better. We're very impatient, I think, of how quickly we want these things. We haven't been doing this stuff very long. You can see the improvements just from the last 10 years. Another step, deep research assistants. These are already being deployed as products. We just, several of those just appeared. And the third, next natural step is AI research assistants. That's being worked on right now. There's a couple of tweets here. So AI2 are working on that. OpenAI just released this paper bench. That's the benchmark for evaluating the ability of AI agents to replicate state-of-the-art AI research. And I think, they already have some models. I think particularly Claude was winning in their benchmark at actually being able to replicate some of these papers. And you have Jason from OpenAI there saying how he's super excited for AI for scientific innovation, which includes AI for AI innovation, a direction I think will grow in the next 5 years. So, of course, there's lots of questions of how to get there. Humans have to remain in the loop somehow, as these models are for humans. We have to worry about hallucinations. You can't modify everything. Something has to be grounded to reality. And there's the world and interactions with humans in the world that can ground things. And, the more the model can modify, the more danger of reward hacking. So it's something we have to understand. And that's
a couple of questions.
Hi, Jonathan. Sonny George from Brandeis. Let's say a model had some sort of negative pathology, let's say, like it didn't understand what a circle is. And let's say your validation benchmarks for the self-rewarding process also didn't measure what a circle was. Perhaps it's judgment that would then serve to be the reward in the training process for situations, let's say, that a circle was pertinent to the situation. It essentially outputted a bad take on what a circle is, and then got rewarded for its bad output about what a circle is. And so because your validation set doesn't really cover all of the possible negative things that the model might have in its set of possible behaviors, what is your response to the possibility of negative things that our benchmarks don't cover becoming amplified through the kind of closed loop rewarding process? Thank you.
Yeah, I think anything can go off the rails. I mean that's kind of what reward hacking is as well, in a way. It's like going off off the rails in a way that we're not really measuring. So definitely one on the list here, the last slide of things we need to deal with. And like I said here, humans have to remain in the loop somehow, I believe, so that we can continue to catch things, and because they're interacting with us. But
so I was wondering how you think about the generalizability of verifiable rewards. So in other words, there are some things where it's very easy to construct programmatic verifiable samples, but other domains where it's not. And so how do you think about the generalizing from that to the other?
yeah, well, I think science should be open and reproducible so that we can do the ablations and get the understanding, rather than, you know, O1 that didn't say anything, and then R1 which has a paper but it doesn't have everything right, like what data exactly they used and stuff like that, so we need to study those things. I think you can make quite a lot of things verifiable, at least to some degree, with, say, multiple choice questions, right? Those are verifiable and they can be in lots of different domains. But it still doesn't cover then, for example, writing a long essay or a poem or something like that. So how much can those, say, multiple choice questions about poems help transfer to writing poems? I think those are interesting research questions that, like I say, I want the academic community to work on so that we can all understand.
Hi, it's Sasha from Yale here. So it's a simple question. So for the meta judge and the meta judge, right, is it aimed to solve the same question as just calibrating our MS judge, or is that designed to do something more than that?
Well, so the meta judge is the same self-rewarding, meta-rewarding language model as the one that's doing the actions. So our hope is during the iterations of training, it's actually getting better at meta judging as well.
Why don't you separate the two? Like again?
Why don't you separate them? Because then it will be fixed and it might not improve. So we showed in the self-rewarding paper and in the meta-rewarding paper that you can actually get better at rewarding as you train. So that's why you don't want a fixed reward model. You actually want your strongest model at rewarding, which happens to be, if you're training the strongest language model acting, I believe will eventually might be the same thing. So that's why you want to do it on itself. Thanks.
One final question.
I'll just make it real quick. For the same reason, I like that idea that you want to have a model that keeps improving as a judge, because building a model based on a pre-built judge is going to limit how much it can actually get. So that approach is really cool. But when you show the graph, it's linear increase, right? It backs our hypothesis, but we don't usually stop when it's still linear. What happens? Are we blocked by computational limitations for it to see the zoomed out picture? I want to know, what are we limited by in this approach? There should be some cap.
They do saturate in performance. The question as to why. You can hit the limit of that model's ability to generalize, right? So that's where you get to.
Other data pressures that is needed external to this hypothesis for it to cross a barrier after the practice?
That kind of goes back to the first question, right, of can it go off the rails, and will it just miss whole distributions of data that then it can't train on? I think yes. So what we're actually missing in this picture I showed is that we let's rewarding one, wherever it is. Let's just do this one. So we actually are training the reward model, we are training the action model, but the generating new prompts thing, I kind of skipped over how we do that. We just do that as self-instruct, so it's few shot prompt of some instructions and then generate a new one. That part we haven't actually, I feel like that's a missing piece. It's how do you make it learn how to make the best tasks? And so that's something for the future.
All right, so let's thank Jason again. Cool. Next, I want to invite our Dean of Engineering, Dean Jeffrey Brock. He's been very supportive of NLP and AI in general, both at Yale and across the region. And I invited him to share a few remarks here. So please welcome me in joining me.
Hello, everybody. Welcome to the former home of the Whitney Humanities Center, which I think is an important signal to the university. We're taking over, department by department, brick by brick. It's really exciting to see such an amazing turnout for this event, and I'm grateful to Armand for his efforts in organizing what is clearly a very popular and sort of cross-pollinating event. I also was gratified to hear the discussion of trying to instruct a computer to recognize what a circle is. As a pure mathematician, I spend a lot of my time thinking about what a circle is, whether it's Euclidean space or hyperbolic space or positively curved space. These are really deep questions. It's sort of not a day goes by when you don't read about this new effort in large language modeling and models to deal with problem solving in a logical and mathematical framework or in a scientific framework, not to mention a linguistic framework. And the marriage of these different approaches to thinking about problems in science and engineering, much less in social science or humanities, I think is kind of a new frontier, and you guys are at the tip of the spear on it. So I want to thank you all for coming, for being a part of this sort of burgeoning and exciting area at Yale, and we're trying to invest in it as much as we can and grow it as much as we can. We hope you'll come back. We hope you'll send your students here, and we hope you'll be a part of the conversation going forward. Welcome to Yale. Thank you.
And next up, we have Yoon Kim. Yoon is an assistant professor at